hi everyone. So we are from Group J, who assigned for a topic of design calculation of the condenser. First thing first, let me give some quick introduction to our topic. The design of a condenser involves a series of calculations to ensure that it can efficiently condense steams and transfer heat to the cooling medium, example, water or air. The design process considers parameters like heat load, cooling water flow rate, surface area, and material selection. So, we do have two content to be presented today, which is the design calculation used for the condenser and examples calculation related to the condenser. To begin with is the design calculation for a condenser. There's few calculations can be done for condenser, and we will focus on these three parts, which is we can calculate the vacuum efficiency, thermal efficiency, and energy balance. Firstly, for the vacuum efficiency, condenser vacuum efficiency is a measure of how effectively a condenser in a thermal power plant achieves the desired vacuum conditions to maximize the efficiency of the steam cycle. Condenser vacuum efficiency is defined as the ratio of the actual vacuum to the ideal vacuum that could be achieved under given operation conditions below, which is vacuum efficiency equal to PHO over P ideal multiplied by 100%, where actual vacuum is the measured vacuum in the condenser, which is in millimeter mercury or kilopascal units, and ideal vacuum is the maximum theoretical vacuum that could be achieved based on the steam's saturation temperatures corresponding to condenser cooling water temperature. Okay, let me dive deeper into the formula of the vacuum efficiency, which is the vacuum efficiency equal to PHO over P ideal, which is equal to P atmosphere minus 2 P total absolute over P ATM minus P saturations. The P saturation stands for saturation pressure of steam entering condenser. P ATM, of course, the atmospheric pressure, and for the PHO means vacuum pressure with leakage, and P ideal is for vacuum pressure without leakage, and the last one is the P total absolute equal to total condenser pressure of air and saturated steam. Okay, next I will share some information about the factors affecting the vacuum efficiency, which is the first one is cooling water temperature, air leakage, steam flow, condenser designs, and falling or scaling. Higher vacuum increase the pressure difference across the turbine, leading to better energy extraction from steam and a more efficient vacuum energy loss, reducing operational costs. Proper vacuum prevents excessive back pressure on the turbine, avoiding damage or inefficiency. Okay, let's move on to the next part, which is calculating the condenser thermal efficiency. Thermal efficiency typically refers to how effectively the condenser transfers heat from the exhaust steam to the cooling water. Thermal efficiency is the ratio of actual rise in the temperature cooling water to the maximum possible rise, which is ideal rise in temperature of cooling water. Thermal efficiency can be described in the formula of actual rise in the temperature of cooling water over inlet temperature of steam minus the inlet temperature of cooling water, where TO means outlet temperature of cooling water, TI means inlet temperature of cooling water, and the TS is saturation temperature of steam corresponding to actual absolute pressure in the condenser. In addition, the factors that are affecting thermal efficiency is the cooling water inlet temperature, cooling water flow rate, steam flow rate, falling and scaling, and the last one is vacuum level. That's all from me. I'll pass it to my other group member to the next part.
Assalamualaikum. My name is Nura Atika binti Muhammad Zari. Okay, next, energy balance. Energy balance refers to the principle of conservation energy, which states that energy cannot be created or destroyed, only transformed from one to another form. In any system, the total energy entering the system must equal the total energy leaving the system plus any changes in energy stored within the system. For a condenser in a thermal power plant, the energy balance can be written as heat gained by cooling water equal heat loss by steam. Okay, Q cooling water, energy leaving the condenser, Q losses, heat loss to the environment. Okay, next, formula energy balance. As you can see, this is the formula for energy balance. Heat loss by steam, heat gained by cooling water. Heat gained by cooling water equal to heat loss by steam. Okay, so for MW, mass of cooling water, MS, mass of steam condensed, H total of steam entering condenser, HF1 total heat in condensate, Ti inlet temperature of circulating water, To outlet temperature of circulating water, Tsat saturated temperature of steam, Ts temperature of the condensate, HFG latent heat of evaporation, and Cw for cooling water.
Next, I will present about section through a typical two-pass surface condenser for a large steam power plant. So this is a schematic of a two-pass surface condenser, a critical component in any steam power plant. Its primary function is to convert exhaust steam from the turbine back into liquid water or condensate for use in the steam cycle. So let's start with section AA, which provide a longitudinal view of the condenser. Here we can see the tube bundle where the actual heat exchange occurs. Exhaust steam flows over the tube while cooling water circulates inside them. This temperature difference drive heat transfer, condensing the steam. Uh, the water box at either end, this distribute the cooling water to the tube and collect it after it has passed through the bundle. The baffle, seen here, direct the flow of steam across the tube, ensuring efficient heat transfer and maximizing the contact surface area. Now, let's look at section BB, a cross-section of the condenser. This view clearly shows the two-pass arrangement of the cooling water flow. The water enters the water box, flow through the tube, make a U-turn, and then passes through a set of tube before exiting the condenser. This two-pass design significantly increase the heat transfer surface area, improving the efficiency of the condenser. In summary, the two-pass surface condenser plays a pivotal role in the steam power plant cycle. By efficiently condensing the exhaust steam, it allows for the continuous and efficient operation of the plant. The design and operation of the condenser directly impact the overall efficiency and environmental performance of the power plant. Okay, next is film condensation on a horizontal tube. This image illustrates film condensation of steam on a horizontal tube. When steam comes into contact with the cooler surface of the tube, it condenses and forms a thin film of liquid on the tube outer surface. This condensate film acts as a thermal resistor, slowing down the heat transfer process. As the film grows thicker, the heat transfer rate decreases. So, temperature rise and cooling water requirement. The rise in water temperature within the tube is typically limited to about 8 to 10 degrees Celsius. This means a significant amount of cooling water is required to condense a given amount of steam. For every kilogram of steam condensed, 75 to 100 kilograms of cooling water might be needed. This highlights the substantial water demand of power plants. Calculating surface area needed. To determine the surface area needed for the condenser, we use the following equation where A is the required surface area, M is the mass flow rate of steam, H2 and H3 are the enthalpy of saturated steam and condensate, U is the overall heat transfer coefficient. Delta T is the logarithm mean temperature difference. Uh, the equation assume a single pass condenser where water flow through the tube only once. In the two-pass condenser, the water make to pass through the tube bundle, increasing the heat transfer area. The number of tube N and the length of each tube is L. Factor that influence the overall surface area of the condenser. Thank you.
Next, I will continue the explanation from Haziq Shami that is related to his slide. So, I'm going to explain the formula of the water flow through the tube, which is measured in kilojoule per second. As you can see, the formula is mass flow rate equal to N. N is a number of tube times pi over 4 times inner diameter of the tube, and times the density and volume velocity. Okay, we break down this formula. The term pi over 4 di is represent the cross-sectional area of a single tube. This is derived from the formula of area of the circle, which is pi r square. Since the radius r is half of the diameter, we can express the area equal to pi di over 2. When we multiply the area of the one tube by number of the tube, we can get the total cross-sectional area of all the tube. This overall, this formula calculate the total mass flow rate of water through all the tube in the condenser. As you can see, for the graph, I will explain how is the plot of 1 over UO versus 1 over V power of 0.8. This plot shown the graph of inverse UO versus inverse VO8. This graph is typically context of reaction kinetic or catalyst, where UO represent a variable reaction such as reaction rate or flux. Meanwhile, V might denote another parameter like concentration or velocity. This graph indicates a linear relationship, suggests that as inverse of V power of 0.8 increase, then 1 over UO also increase. This relationship is increased proportionally. The intercept of point A and the slope of point B help in deriving the important parameter related to the system being studied, such as kinetic constant and efficiencies in condenser. From this graph, we can analyze to deduce how the changes parameter affect another, helping to optimize and control the experimental condition. So we move to another slide. So we look the first formula, which is the pressure drop due to the friction in the tubes. Okay, this is the Darcy-Webash formula from my research. For the F is represented as friction factor. Next, L is length of the tube. D for diameter of the tube, measured in meters. Rho is density of the fluid, which is measured in kilogram per meter cube. For example, like water is typically around 1000 kilogram per meter cube. For V is the velocity of the fluid flowing through the tube. As you can see, this formula is derived from the principle of fluid dynamics, specifically Darcy-Weisbach equation. Moving to second formula, which is the pumping power required. P equal to mass flow rate condenser times velocity times the pressure difference of the pump equal to mass flow rate condenser times pressure difference and over density. By understand the power required from pumping, we can select the appropriate pump for a system and minimize the pressure drop in the system due to friction and other losses. Based on the graph temperature profile in a condenser, we can observe the temperature profile of steam and cooling water within a condenser. The horizontal axis represent the flow of heat, while the vertical axis indicate the temperature. The steam enter condenser at high temperature, which is Tsat, and as it condenses, it releases heat, causing its temperature to remain relatively constant until it reaches temperature T2, TC2. Meanwhile, the cooling water enter at TC1 and absorb the released heat, rising the temperature, and it flows through the condenser until it reaching the TC2. Okay, TTD. What is TTD? TTD is temperature terminal difference that represent the gap between Tsat and TC2, which reflect the efficiency of heat transfer process. The smaller TTD indicate the more efficient condenser. This graph allow us to visualize how the cooling water temperature increase due to heat absorption and how the steam reach its saturation and condensing phase. I think that's all from me. That's all from Group J. Thank you.
Okay, now we are going to talk about the example. So for this example, we need to determine the vacuum efficiency, thermal efficiency, mass of cooling water, logarithmic mean temperature difference, and surface area of condenser. So for the steam inlet condition, the mass flow rate of the steam is 20 kg per second. Inlet steam pressure is 7.197 cmHg. Inlet steam temperature is 45 degrees Celsius. The enthalpy of inlet steam is 2583.2 kilojoule per kg. So, for the condensate outlet condition, the outlet condensate temperature is 35 degrees Celsius. The enthalpy of condensate is 146.68 kilojoule per kg. So for the cooling water condition, the inlet temperature of cooling water is 25 degrees Celsius. The outlet temperature of cooling water is 35 degrees Celsius, and specific heat of cooling water is 4.186 kilojoule per kg by Kelvin. So for the vacuum pressure in condenser, the actual vacuum pressure is unknown. The ideal vacuum pressure is unknown too. The atmospheric pressure is 1.013 bar, which is equal to 76 cmHg. The condenser vacuum is 70 cmHg. So for the additional data, the heat transfer rate is unknown, and the overall heat transfer coefficient is 2.5 kilowatt per meter square by dot degree Celsius. So for the solution, first we are going to find the vacuum efficiency. Vacuum vacuum efficiency is to see how efficiently the condenser maintains the desired low pressure condition. So for the absolute pressure is 10 cmHg, and the actual pressure is 66 cmHg, and the ideal pressure is 68.803 cmHg. So for the vacuum efficiency, the the formula is P actual divided by P ideal. So the efficiency of the vacuum is 95.9%. Then we are going to calculate the thermal efficiency. Thermal efficiency is to determine how effectively the condenser transfer heat from the steam to the cooling water. So the formula is uh, temperature outlet of cooling water minus temperature inlet of cooling water divided by temperature of steam minus by temperature inlet of the cooling water. So the thermal efficiency is 50%. Next, we are going to calculate the mass flow rate of the cooling water. This determines the amount of cooling water required to remove the heat rejected by the steam. So here, Q dot steam is equal to Q dot cooling water. So the formula is mass flow rate of steam multiplied by uh, enthalpy of steam minus enthalpy of condensate is equal to mass flow rate of cooling water multiplied by heat specific heat capacity of cooling water multiplied by temperature outlet of cooling water minus temperature inlet of cooling water. So the mass flow rate of cooling water is 1164.128 kg per second. So next is we are going to calculate the logarithmic mean temperature difference. This is calculated to assess the effective temperature driving force for heat transfer in condenser. So the formula is delta T2 minus delta T1 divided by log delta T2 divided by delta T1. So for the delta T1 is the temperature of steam minus temperature of cooling water at the outlet, and for delta T2 is temperature of steam minus inlet temperature of cooling water. Yeah. So the logarithmic mean temperature difference is uh, 14.43 degrees Celsius. So for the last is the surface area of the condenser. Uh, the surface area is surface area that require to the for the condenser. So the formula is Q dot of cooling water is equal to UA multiplied by uh, logarithmic mean temperature difference. Uh, so for the Q dot of cooling water, the formula is as above, which is mass flow rate of cooling water multiplied by specific heat capacity of cooling water, then multiplied by temperature outlet minus temperature inlet of cooling water. So the Q dot is for 48,520.855 kilowatt. So then we put that into the formula just now. So the area is 1,345 meters square.